Continuing our study of limits, now we talk about limits at a point. Before we actually get there though, I do want to introduce one important concept when we talk about functions. So one important property of a function is if a function is continuous, or if it's not continuous, we say it's discontinuous. Now, technically we need a little more mechanics to thoroughly, or not thoroughly and rigorously define what continuous and discontinuous mean. So right now what we're going to do is just kind of give a heuristic definition. So if I were to draw a continuous function, it should be drawn so that there's no holes, gaps. Gap is change in domain values, so there's a chunk of the domain that is missing, and a jump I'm defining to be a gap in the range values. Okay, and so if it does not have those, then it will be continuous. And so really what we're thinking about a continuous function being is if you draw it, your pencil should not stop or lift off the paper. Okay, so for example, a basic parabola is a continuous function because I can draw it and it'll continue. Now keep in mind that it's okay if I don't hit every single range value, but the range values in between here should all be hit. Another continuous function is our basic exponential curve. Okay, so something like that. Another continuous function is our graph of sine and cosine. Okay, so let's see, sine starts at 0 and increases, decreases, increases, da 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 da. Okay, and both ways forever. Alright, now examples of something that might be discontinuous. This might be a piecewise function. Not a piecewise linear function, but a piecewise function. So it could be something that looks like this, has a hole, jumps up, circle, then another hole, increases like a square root, and then closed dot, comes down here, straight line, open circle, closed circle, and this would continue. Something like that. Okay, so there's gaps in the domain. Actually, there's no gaps in the domain, but there's a gap in the range. Okay, holes, etc. Okay, and so another example might be just typically you see discontinuous functions as piecewise functions. So you might have the origin go down here, and then have another value that comes up here and continues up like that. Here you're missing range values. This is a jump. Okay, so brief rundown on continuous versus discontinuous. Now we're actually going to start determining limits at a point. Okay, so if we use these couple nice properties, the constant property, so if you have a limit and it's of a constant, it's just the constant, and then the direct substitution property, this is where the continuous part comes into play. So it says if C is a real number, okay, and f is a continuous function, then we can actually substitute in the limit value into the function and get out our value for the limit. Okay, so for example, limit as x approaches to natural log of x minus 1. Now here we know the log function, natural log function, is continuous on its domain, meaning that the inputs, this chunk, has to be greater than 0. And so if I solve this, the domain is going to be x is greater than 1. 2 is within that domain. Okay, so I can use a direct substitution property and get natural log, the limit being the natural log of 2 minus 1, which is the natural log of 1, which is the same as 0. Okay, next problem. The limit as x approaches negative 3 of this. Okay, and so we first have to think, okay, well, C, real number, okay, that's good. And now f has to be a continuous function, okay? This is a basic exponential expression, horizontal translation, or horizontal reflection, sorry, and a vertical shift, okay? Still a continuous function, okay? Just because there were two basic transformations that were applied to it. So I use the direct substitution property, 1 plus e to the negative 3, or just 1 plus e cubed. That's all it is. Alright, and the last problem. Alright, so we look at this thing, and we see a limit as x approaches 3 of this rational function. Okay, now a rational function will be continuous, i.e. it will be a smooth curve on its domain again. And so we know that the domain here would be undefined whenever the denominator is 0. Okay, and so if you set that equal to 0 and solve it, you actually end up with the domain being equal to all real numbers except the set 3 and minus 3. Okay, so what do we do now? We can't use the direct substitution property as it is. However, I see there's a 2 in common in both of these, and I know the denominator factors, so let's just try some basic algebra on it and see what happens. So the limit as x approaches 3 of, and now I'm going to factor out that 2, x minus 3, and the denominator factors as x minus 3 and x plus 3. Okay, and well, these factors can cancel, and so I can write this as the limit as x approaches 3 of 2 over x plus 3. Okay, so this cancellation, remember when we do this in a rational function, that creates a hole in the graph. And a nice thing about a limit, like I said before in our previous videos, is it gets ever closer to that value, but it does not attain that value. So we actually don't need the function to exist at 3. It just needs to get really close to 3. And so now with this is continuous. It's undefined at -3, but that doesn't matter because I'm approaching positive 3. So I can use the direct substitution property and get 2 over 3 plus 3. And simplify this, that's 2 over 6, just down to 1/3. Okay, so again, if the direct substitution property fails you right away, try some algebra on it, try factoring, and see what you get. Oftentimes something will cancel. Okay, so now we have this problem. We have the limit as x approaches 0 of 2 over x squared. Okay, well, this one, I can try the direct substitution property, but it's not continuous at 0. There's an asymptote at 0. That's not good. I can't factor it, so what do? Well, we actually need to talk about one-sided limits, so left and right-hand limits, as we as we come in from the left and as we come in from the right towards a value. And so what we want to think about is on a number line, here's our value of c, the limit, the real numbered constant that the function approaches. Okay, so as we approach from the left-hand side, we denote that as x approaches c with a superscript of a minus sign. This is not an exponent, it just means the direction from which you're coming. So this limit refers to coming in this way towards c. On the other hand, the right-hand limit, x approaches c with a superscript of plus, means that you're starting at a positive number that is larger than c and coming in ever closer to the value of c. Okay, and so oftentimes when you do this computation, it's best to compute these numerically, meaning through a table. And so I did that, and for our problem up here, this is the limit or the values of f of x as you get close to 0 on the left-hand side. So again, we're thinking if this is 0, coming in from the left, we're negative, but really, really close to 0. So I started at 10th, go to 100th, 1000th, 10,000th. And we see we get more and more positive. So I say that based on this table, this limit is going to approach positive infinity as I get closer to 0 on the left-hand side. Now on the right-hand side, I did the same thing, and I end up getting positive infinity as well. Okay, and a nice property of the left and right-hand limits is if the left and right-hand limits approach the same value, okay, so they approach both infinity, then that is then the actual limit as it approaches 0, just plain with no superscript, is actually equal to that value, okay? And vice versa, okay? So if you know the limit at a number is true, then the right and left hand limits have to agree. So we can say that our original problem, this is actually equal to infinity. All right? So left and right hand limits come into play quite... Okay, so in this video we've looked at computing limits algebraically, numerically, and the last one we're going to look at is a graphical approach to computing limits. So here's a graph of f of x, okay, and we're being asked to find these different limits. So as it approaches -2 from the left, okay, so here's -2, and I'm coming in from the left, so I'm in this branch of the piecewise function, and I see that as I approach -2 from the left, I get stuck down here. I can't actually jump up here. So this is equal to, let's see, a -3. Then if I approach from the right, okay, I'm coming in, okay, come up here, and I get closer, and I get stuck here. I can't actually jump down here. So the limit here, as I approach -2 from the right, is actually at 0. Okay, and so the limit at And now I'm going to look at the limit as I approach 2 from the left. Okay, so I'm coming in, starting over here, go down here, come up here, and I get stuck at +2 at this hole. I can't jump down. Okay, so I have to stop it wherever I get stuck. And this is going to be 2. As I come in from the right, I'm going to get stuck at -4. Alright, and now I want to evaluate the function at 2. So I go to, sorry, this should be, okay, 2, and then this one should be -2. Alright, so if I evaluate the function at +2, okay, I'm looking at 2, and I'm looking for where there's a closed dot. So this is 0. Alright, and similarly at -2, I look here, where's the closed dot? That's at -3. Alright, one last note is if I were to just say, let's look at the limit as x approaches 2 of f of x. Alright, so I want to know what is the limit at f of x. Well, I have to look at the right and left hand limits. They do not agree, they are not the same value, so I actually have to say that since they are not equal, this limit does not exist, DNE. Alright, so basic rundown of limits at a point, algebraically, numerically, and graphically.